Students of ECGO 3157 Junior Design were tasked with completing Lab 6. This lab was basically a culmination of all our work throughout the semester.
Yeah, so the scope of this project included simulating the circuit model that we were going to be building on the PCB, actually designing the PCB and ordering it, then finally testing and getting the results of the testing of the actual constructed PCB.
So this here is our first PCB design. This was designed by everyone in the group except for Mikey, as Mikey was the only one in the group who had experience designing PCBs before. In this design, there's a clear lack of basic design principles for a functional PCB as our first attempt.
This was the second version of the design that was designed by me, and as you can probably see, it's a more linear approach and it follows the design schematic a bit better. It also is only 2 layers and is overall the design we chose to go with.
With our design completed, we consulted PCB Way and got an estimate for what it would cost to order 5 boards. We decided to go for 5 because it made the total order a lot cheaper than if we had just gone for a single. But also, in the case that something had happened with one of the boards, we would have a few extras.
Calculations were done by Cordell, Gideon, and I. For the current sensor, simple voltage dividers were used in order to get proper output according to the design parameters. For the voltage sensor, besides using a voltage divider at the input stage, we also had to develop a transfer function for getting our output. There was one main issue with this schematic that we found. The initial requirements were that we had to have a 0 to 3 volt unipolar swing out on the voltage sensor. This, however, created a problem because we thought initially that we had to integrate this to the microcontroller, which could damage it, but we later found that was not correct. The fix for this, though, would be to change the ground in at resistor 9 to an input voltage. The output of the current sensor was, however, 0 volts to 3 volts, as the project requirements required.
Comparing some different sites, we got the cheapest total cost and having the widest component selection from DigiKey. So after ordering the components, we had a total cost, as seen on the slide, a little over $42. So it's perfectly manageable.
The board was populated by Mikey and myself. There were a few hiccups while getting the components onto the board. Precisely, we cracked 2 of the capacitors that we had ordered, and we needed to source separate capacitors because we didn't really have time to wait to order more capacitors. Another problem we had while designing it was Mikey, who was also doing it, dripped molten solder onto his foot.
Our group lead said that he wanted to have this inside the PowerPoint, but I decided I'm not going to give him a picture of my foot for a PowerPoint. That sounds a little weird. Yeah, it definitely hurt when it happened.
With everything soldered and Mikey sufficiently injured, we decided to take a picture. However, now because we had cracked 2 capacitors for surface components, we instead had to, on the fly, use a few through-hole components where we had clipped the leads and soldered them to the boards since we wouldn't have to wait for new capacitors to arrive. Testing of this board was completed by our group leader, Fish, and the one who had the most experience with the board, Mikey. At the discretion of the TA, Section 2B of Lab 6 was skipped, and if the board worked with the microcontroller integration, we were ready to hook it up and use our power electronics module located in the free lab of EPIC. The microcontroller and PCB board was connected to the module as seen in the following images.
The code was developed in MATLAB Simulink using a discrete sign block that was instead using time-based, we had to use sample-based signs. The microcontroller is a discrete system, so the system would perform better when using simple-based time. The period not needed to operate was 1/60 Hz. As you can see from the results, there is a lot of noise in the system from just the output. The top image shows the current sensor's output. It has a very small gain compared to the input, but this is what we wanted, and it is also completely above 0 volts, so it would prevent damaging to the microcontroller. Whereas the bottom image shows the output of the voltage sensor. The output was very small, but this is exactly what we wanted, as we did not want to have any damage when operating this, even in an open loop.
So when we actually implemented the closed loop on MATLAB, we made sure based on the output, feed it back and then compare it to a reference voltage before putting back into for the duty cycle modulation.
So here are our closed loop results. They are much less noisy than what they were in the open loop results. These are a couple of test points. Our reference was doubled in between them so that we could see that it was stable across multiple different reference points. This is the transient response, basically when it changes from one state to another with the reference current. So on the left we have one that's half the strength as what's on the right, and as you can see, it quickly corrects and quickly allows for it to change voltages across the system.
Lab Report 6 was written by Cardell, Gideon, and myself. The PCB performed much better than we expected for how cheap the PCB was, as well as the components. And the components all worked effectively, including the 2 through-hole capacitors that we had to source. The whole team really came together and worked hard on this final project. We've all learned a lot, and overall it was just a really enjoyable experience.